Hey, this is lecture 18. I'm going to give a little bit of the terminology for discrete time Markov chains. So that's why it says part 1. Part 2 will come next week. Okay, so just a reminder, in the previous lectures we talked about a one-step transition probability. So this is the probability that you're in state I at the present time, and the probability that you're going to move to state J in the next time step. Okay, so here, if Pji of n is just a constant, it does not depend upon n or the time, then it's said to be stationary or time homogeneous. Or you can actually think of just saying homogeneous. So if it is time dependent, if it truly is that Pji of n does depend upon the time, is time dependent, then it's non-stationary or called non-homogeneous. So just a little bit of terminology here. Okay, so recall that if you're adding up the sum of the columns, they should sum to 1, and that all probabilities are greater than or equal to 0. So it's between 0 and 1. So here we have the transition, the probability transition matrix that we talked about last time. So this is the probability of going from state 1 to state 1 or state 1 to state 2, for instance. If the states are finite, then P is an n by n matrix. Okay, so remember we always have that the column sum is 1, the way that we write it, the way that Linda Allen's book does it. And so in this case, P is called a stochastic matrix because we have column sum is 1. Sometimes we also have the row sum is in addition to the column sum also 1. So if both the row sum and the column sum are both 1, then it's called doubly stochastic. So moreover, if you have P as a stochastic matrix, so again it's like a transition probability matrix, then P to the n is also a stochastic matrix. So remember we used P squared and P cubed in our examples to calculate what would happen on the second month or the third month or the second day or third day. And so here we have that the probability of I to j to the n is the probability that in the nth time step you're in j, given that you start in I. So this is what it means. This is what the matrix means when you're talking about Pij of n. And here you just have Pij of 0 is the delta ji, which is just 1 if j is equal to I and 0 if j is not equal to I. So basically, your P to the 0 is just your identity matrix. So you can think about that in terms of just linear algebra and matrix multiplication. Any matrix to the 0 power is just identity. Okay, so now we want to talk about how to classify states. So this is an example. So we have 3 states here. We have I, j, and k. And so here if you're in state I, you have a possibility of going to state j. If you're in state j, you could go to state k. If you're state k, you can go to state j. So there's a non-zero probability. If there's a non-zero probability, so P going from I to j in some transition, so there is some n here, so that this probability of going from state I to state j is positive, which means I can basically get from state I to state j in a certain number of steps. That's basically what this means. If this is positive for some n, then it means that state j can be reached from state I. If that's the case, then state j is said to be accessible from state I. So here, I can get to state j from state I. So in this diagram, obviously I can get to state from state I to state j. That's the only thing I can do. That's the only transition I can make, right? The way that this transition matrix, even though it does not have the probabilities associated with it, there's nothing else that you can do when you're in state I other than go to state j. So this would be a probability of 1. So the probability of going from state I to state j, so Pji, is positive, and in fact it's equal to 1 in this case. We also have I can go to K. So here, if you're in state I, then you have to go to J. That's your only possibility. If you're in state J, then the only thing you can do is go to K, right? So here, in 2 steps, I can get from I to K, which means that K is accessible from I. And I also have that K is accessible from J, and J is accessible from K, because if I'm state K, I can go to state go to state J. If I'm in J, I can go to K. And I do this in 1 step. Okay, so if I can be reached from J, then I is said to be accessible from J. So the terminology here is that they communicate if both of them are accessible to each other. So if I can go to J, and J can also go to I in some probability, so if they're both accessible to each other, then they are said to communicate or to be in the same class or equivalence class. And it's denoted by this double arrow. So here, this means J is accessible from I. Or if I'm in state I can go to state J. So if I have both of them, if I have J is accessible from I, and I is accessible from J, then I say that they communicate. So this is the terminology for they communicate. It means that there is some time step, it doesn't have to be 1, but at some time step there's a positive probability that I'm going to get to state J from state I. And there's a positive probability in some time step in prime here that I can go from state J back to state I. So in this example, J and K communicate, but notice I and J do not. So I and K also don't. So here, K is accessible from I, but I is not accessible from K. So if I start in K, there's no way of getting to I. So K and I don't communicate. Okay, so if they communicate, if I and J communicate, then this is called an equivalence relation on the state space. So basically what this means is I communicating with J, it has this reflexivity property. So I always communicates with I because I start there, right? So if I have PII to the 0, I'm in state I to begin with, so the probability that I started there was 1. So if I communicates with J, then obviously J communicates with I. It's just given the definition of it, so you have symmetry. And the other reason why this is said to be an equivalence relation is this transitivity property. So if I communicates with J and J communicates with K, then this has to imply, so I is accessible from J and J is accessible from I. J is accessible from K, J is accessible from K and K is accessible from J. So it obviously means that if I'm in I can get to K, or if I'm in K, I can get to I. So that means I and K have to communicate. Okay, so the set of equivalence classes in a discrete time Markov chain are called communication classes, or classes of the Markov chain. So if they communicate, they're in the same class. If every state can be reached from every other state, then there's only one communication class. So in this example, notice that J and K communicate, but I does not. So in this case, J and K is a communication class because they communicate, right? But I is by itself. I doesn't communicate with any other states. I goes to the state, but it doesn't communicate with it because I can't get from J back to I. Okay, so an example, let's look at this one. So here we have 4 states, 1, 2, 3, and 4. So if I look at this, what I have, so look at what I have. 1 can go to 2, 2 can go to 4 and 4 can go to 2. 3 can go to either 1 or 2. So if I think about what can communicate, 2 and 4 are the only ones that can communicate, right? So I can go from 2 to 4. I can also go from 4 back to 2. So here, 2 is accessible from 1, but I can't get to 1. I can't get back to 1 from 2. So if I start here at 2, there's no way of getting back to 1. So 1 and 2 don't communicate. If I'm in 3, 2 is accessible from 3. So that's here. 2 is accessible from 3. But if I'm in 2, there's no way of getting back to 3. So they don't communicate. And here, 1's accessible from 3. But again, if I'm in 1, there's no way of getting back to 3. So these are single communication classes. So we have 2 and 4 in one class. 1's by itself because it doesn't communicate with anything else. 3 is by itself because it doesn't communicate with anything else. And here, this is the probability transition matrix. So remember, this is my current state. This is my next state. So here, if I'm in state 1, I can go to state 2. If I'm in state 2, I can go to state 4. So here's this. If I'm in state 3, I can go to 1 or 2. So here, if I'm in 3, I can go to 1 or 2. And if I'm in 4, I can go to 2. So that would be the non-zero one. And at least on these, we can figure out what they are. This has to be a 1, this has to be a 1, and this has to be a 1 because the column sums have to sum to 1, and all we know is that these two have to sum together to be 1. Okay, so next time we're going to talk about a little bit more terminology for the discrete time Markov chains.